All right, what's up, guys? Mr. C here with our next lesson, lesson 8.3. You're going to be going a little bit more in depth with rational functions. Yesterday, we kind of went over the basics about asymptotes and such. But really, when you start to dive into rational functions, they can get a little bit complicated. There's a lot of different types of rational functions. There's a lot of different parts that we need to remember of rational functions. And before we go over anything, I do want to take a look at just a couple of graphs of rational functions just to show you that they can all indeed look quite different. So let's look at these. Okay. Here are three examples of rational functions, and as you can see, the shapes, it's not like they're all parabolas, like quadratics are all parabolas, or they're all lines, like linear equations are all lines. They all have very different shapes, and there's different reasons why these all have different shapes. For example, this one, you're never, for any value of x here in the denominator, you're never going to divide by 0. X squared plus 1, no matter what value of x you put in, you'll never get 0 in the denominator. So that's one reason why you don't have any vertical asymptotes here. This one is a little bit different. We have a whole rather than a vertical asymptote. So you can divide by 0 here. For example, if x is negative 2, okay, because negative 2 plus 2 is 0, and you'd end up dividing by 0 when x is negative 2. But you don't have an asymptote. The reason is because I don't know if you guys can hear, but my son is yelling upstairs. That's why I'm laughing. Anyway, um, oh my gosh, this is hard. This is hard working from home. Anyway, because you have the same factor on top and on bottom, which is why you have a whole instead of a vertical asymptote. And then this one, of course, looks a little bit more like what we're used to. So we're going to go over, don't worry, on how to find these things and such. But let's start with points of continuity. All right, I want to talk about, or sorry, point of discontinuity. Points of discontinuity. Okay. Now, basically, this is wherever our denominator is going to be 0. Okay. So solve the denominator for 0. Those are points of discontinuity. And there's two different types of points of discontinuity. There's removable, and then there's non-removable. So here's what I mean by removable versus non-removable. If you have a removable type of discontinuity, that would be an example like the one we looked at earlier. This is x plus 3 times x plus 2 over x plus 2. And the reason we refer to this as a removable type of discontinuity, because the original equation, x plus 3 times x plus 2 over x plus 2, this technically, if you're dividing x plus 2 over x plus 2, can kind of cancel. But in the original equation, you do have x plus 2 in the denominator. So if you tried to plug in negative 2 plus 2 is technically 0. But there's a difference between 0 over 0 and then some other value over 0. 0 over 0 produces a hole in the graph, whereas any other value produces over 0 would produce like an asymptote, vertical asymptote. So this is why we refer to this as removable, because you can cancel the x plus 2's. So this produces a hole at x equals negative 2. However, a non-removable okay, a non-removable type would be like y equals x plus 4 over x minus 2. Okay, if we're trying to figure out where my points of discontinuity are there, all you're doing is taking the denominator, saying, okay, where is that going to be 0? You can solve that easily by saying x is going to be 2. So we don't have a hole there, we have a vertical asymptote. Reason being is because the x minus 2 is not cancelable, it's not removable. Basically, we don't have a factor of x minus 2 on top, just like we do on the bottom, like we did in the case up here for x plus 2 appears on top and on bottom. So that's what I mean by removable versus non-removable. So this would be a vertical asymptote at x equals 2 in this case. Okay, so let's go ahead and practice one of those. An example, if I said find the points of discontinuity, all right, find the points of discontinuity, and here's my equation, y equals x plus 3 over x squared minus 4x plus 3. Okay, so here's what you'd be given in a problem, an equation, and we want to find the points of discontinuity. Okay, so I'd mentioned take the denominator, set it equal to 0, and let's solve that. So just this portion, I don't have to be worried about the x plus 3 when I'm solving this on top. So x squared minus 4x plus 3 equals 0. And if you recall, this is quadratic, so we need to either use quadratic formula, factor, something along those lines. Looks like I can probably factor this to an x minus 3 and x minus 1, right? Because we have an x squared minus 1x minus 3x, that's the minus 4x, and then a positive 3. And if we're solving this, we have an x equals 3, and we have x equals 1 coming from these two factors. Okay, this produces a solution of 3, this produces a solution of 1. So there is where our asymptotes are going to be. Now, are these removable or non-removable? These are both non-removable. You might be tempted to see the positive 3 here and a positive 3 here, but what actually produces a 0 on top? It's when x is negative 3, right? So you can see here, if I write it in factored form, okay, we don't have the same factor on top as we do bottom, right? So there's going to be no removable types. Okay, these are going to be both non-removable at x equals 3 and x equals 1. Okay, so 2 points of non-removable. All right. Okay. Hope that's clear. Let's just do one more example before I cut it off for Wednesday's portion of the video. So let's do one more. All right. Let's try this one. But we're going to have a couple more directions because this is what it's going to say on the homework. Find, and there's quite a few things to find. Find the domain. Points of discontinuity. X, ints, and y ints. Okay. These are all the steps you're going to have to do in some of the problems for homework. So 4 parts. Find the domain, points of discontinuity, x ints, and y ints. And you'll find that domain and points of discontinuity are pretty well connected. So here's our equation. Y equals x squared minus 3x minus 4 over x minus 4. Okay. So first question. Domain. Remember, domain represents what values of x can I plug into this equation and have there be no issues with it. And we've pretty much just been already answering those questions. And if we find the points of discontinuity, that's telling me where my domain is basically. So you can already see it's in factored form on the bottom. I just have an x minus 4. Okay. So we know x minus 4 cannot be 0 because I can't divide by 0. Okay. So x cannot be 4 if I'm talking about my domain. All right, I hope that makes sense. The only number I cannot plug into this equation will be 4 because I'm not allowed to divide by 4. You'll see there's a vertical asymptote there, or maybe there's a hole, depending on how the top factors. But if we're doing domain, okay, there's really a lot of different ways. Students really struggle with how to write domain. We just need some way to communicate what values of x can I use. So you could use inequalities, you could use an interval. You could really say all real numbers, if you guys remember going over sets of numbers, you could say it's any real number, but x cannot be, what was it, 4? X cannot be 4. That's one way you can write domain. Okay, just tell me what values x cannot be. You could write it as an inequality or an interval. Like you could say x is from negative infinity to 4, and then from 4 to infinity. And if that looks confusing, basically all this is saying is that from negative infinity to 4, and when we use these curved brackets, we're saying we cannot include these numbers. Okay, so all numbers between these two and all numbers between these two. And really, this is just another way of saying anything but 4. Okay, you could say that's one way, second way, third way. You could say x is less than 4 and x is greater than 4. Okay, that's a way you could use inequalities. And honestly, I don't care whatever you do. Usually students gravitate to this because we've been working with inequalities for a while, probably since middle school. So this is fine. Any of these, I hope you understand each of them. But yeah, x cannot be 4. That's my domain. And then that's also kind of my discontinuity, but I want to explain not only where the point is, but is it removable or is it non-removable? So in order to answer that, we need to see, does this factor of x minus 4 occur on the top too? So if I factor the top, okay, this is going to factor to an x minus 4, x plus 1. And I hope that answers our question. I hope you guys see that that does answer our question. Is this removable or is it non-removable? And the case is that it's removable because I have the same factor on top as I do on bottom. So that answers my domain, points of discontinuity. We'd say removable at x equals 4. Okay, so that answers that portion. Okay, removable at x equals 4. And then lastly, we need to find our x and y intercepts, which we've really been doing since the beginning of the year. Remember, x-intercept is whenever y is equal to 0, and y-intercept is whenever x is equal to 0. And those aren't really that bad solving, figuring out for rational functions. Okay, let's find my x-intercept first. Remember, that's when y equals 0, and then solve for x. So if I was to say that 0, plug in 0 for y, equals x squared, what was it, minus 3x, minus 4 over x minus 4. Okay. Nice thing about rational functions is if you're solving for the x-intercept, you can really just multiply both sides by x minus 4 and 0 minus x minus 4. It's almost like you don't even care about the denominator. Really, if you want to get something to equal 0, as long as the top is 0 and not the bottom, then you know you've solved it. So multiply both sides by x minus 4, and that basically will just continue to be 0 equals, and if I write this in factored form, x minus 4, x plus 1. And if it's already in factored form, we should be able to solve this. We should have one at x equals 4 and x equals negative 1. Okay. But one of those we already have an issue with because we know it's not continuous here. So we know it's not going to go through this point because we have a point of discontinuity. So we're not going to count that 4. don't count the 4, but we do have an x-intercept at the point -1, 0. Okay, we have an x-intercept there. That's one of them. Okay, and then y-intercept, that's when we plug in 0 for x and solve for y. So I should have y equals, if we're plugging in 0 for all these, 0 squared minus 3 times 0 minus 4 over 0 minus 4. Right? That's 0, this is 0, this is 0. So you're basically left with -4 over -4, which is 1. So you should have a y-intercept at, whoops, we're doing the y-intercept, not the x. It should be 0, 1. Okay. 0, 1 is my y-intercept. So I know there's a lot to that problem. Again, domain and points of discontinuity are very closely connected. Even the x-intercept, well, at least in this case, because it was removable, we had to cancel the x-intercept and then y-intercept, plug in 0 for x and solve. So these are process for finding x and y-intercept are always the same, really no matter what kind of equation you use. It's always plug in 0 for y, solve for x, or plug in 0 for x and solve for y. But let me know if you have any questions on this stuff, guys. This is where we're going to stop for Wednesday's portion of the lesson. I'm going to continue on just in a moment and continue to teach the rest of the lesson for Thursday. So again, leave me any comments, questions that you have for Wednesday's lesson. And here comes what we're doing for Thursday. Okay, so let's go ahead and get started on Thursday's lesson. Yes, son? You need to stay upstairs for a moment, bud, till I'm done with the lesson, all right, dude? All right, let's continue. Okay. Well, the only thing we're going to do on Thursday is finding horizontal asymptotes. Okay, so finding horizontal asymptotes. Okay. And there's actually a couple different cases. Okay, a couple different cases. So we're going to look at this. Y equals, we'll say x to the m over x to the n. Okay, and this might look kind of confusing. And here's what these m and n represent. M is the degree of the numerator. And n is the degree of the denominator. Okay, so we have the degree of the numerator, degree of the denominator. Okay. Now, in order to find the horizontal asymptote, there's a couple different cases. There's really 4 of them. They depend solely on what m and n are. Okay, and if you forget what degree is, let me explain again. Remember, if you have a polynomial like y equals x to the 5th plus 4x to the 3rd minus 2x minus 7, something like that polynomial. Remember, degree refers to the largest exponent. So this example here would be a polynomial of degree 5. Okay, of degree 5. So that's what I mean when I'm talking about degree. Okay, so there's a couple different cases. All right, the first one is when m is equal to n. Okay, well, let me write case 1. Okay, and this is m is equal to n. Okay, so an example would be like y equals 2x to the third minus 2x squared minus 4x plus 7 over 3x to the third plus 2x minus 4. Okay, something like that. And remember, I'm saying when m and n are equal, and what are those? Those are the degrees. So this is degree 3 on the numerator, and this is degree 3 on the denominator. And when I'm finding a horizontal asymptote, and the degrees are equal, okay, what we want to do is take the ratio of their coefficients, of the leading coefficients. So this 2 and this 3, that's where I'm going to get my horizontal asymptote. Okay, the horizontal asymptote is, in this case, y equals 2/3. Okay, y equals 2/3. That's my horizontal asymptote. And again, what am I referring to? Is that this graph, if this is, okay, if this is 1 here, that means I have a horizontal asymptote basically at 2/3 that this graph is going to follow. Okay, I don't know exactly what it looks like because there's a bunch of other things you need to find, but that's what I'm referring to. Okay, so if the degrees are the same, okay, divide their two leading coefficients. So this is 2, this is 3. That's where you're going to have your horizontal asymptote, right? That's the first case. Next case, case 2. Okay, this is when m, so that's the numerator, that's less than the degree of the denominator. Okay, when m is less than n in this case. So an example would be y equals x plus 2 over x squared minus 7. Okay, that's an example where the numerator, the degree is 1, right? M is 1. In this case, n is 2. Degree of the denominator is 2. It's less. M is less than n. So this is pretty easy. There's not really anything to do. All you need to do is recognize that. And then the horizontal asymptote. Okay. Horizontal asymptote is just y equals 0. Okay. And it's always that whenever m is less than n. Okay. If the degree of the numerator is less than the denominator, you have a horizontal asymptote at y equals 0. Okay. That's my second case. And then case 3 is nice. Case 3, this is when m is greater than n. Okay, so an example where m would be greater than n is if we had like y equals, I'll just take the reciprocal of the last one, x squared minus 7 over x plus 2. Okay, then there's no horizontal asymptote. Okay, so again, 3 cases. Case 1, if they're congruent, m and n are equal, divide their leading coefficients. Right? If the top is less than the bottom, it's always y equals 0. And if the top is greater than the bottom, there's no horizontal asymptote. There's really one other case where you can have like a slant, okay, but we're not going to go over that this lesson here. We'll go over that later. But these are the 3 cases we need for this lesson, okay? So we're going to go ahead and do an example, kind of put everything together, and then we will call it a lesson, all right? We'll call that done with 8.3. So let's try this next one. Okay, I'm going to say graph in detail. And we have y equals x squared plus x minus 12 over x squared minus 4. Okay, x squared plus x minus 12 over x squared minus 4. Now, what I mean by graph in detail is everything that we just learned how to find, all the holes, the vertical asymptotes, the horizontal asymptotes, the x-intercepts, the y-intercepts, I want those to be shown on this graph. Okay, so we really haven't done very much graphing in detail. Usually I like to skip a lot of that stuff just because it's pretty straightforward. But these ones, the reason we would do this is because these things don't show up on your graphing calculators. Okay, it's not like I can just plug that right in and figure out where the holes are. Okay, you really need to know what's going on with these rational functions in order to understand what you're looking at in at least a graphing calculator. And there's stuff you miss that the graphing calculator won't tell you. Okay, that's why we're doing these in detail. I know you guys are super excited because you love graphing, but let's go ahead and go through all the things we just went over. So first thing to do would be a good idea is to factor it to see where you're going to have a hole and where you're going to have a vertical asymptote. Okay, so let's factor this out. The top looks like it'll factor to an x plus 4 and an x minus 3. That's x plus 4 times x minus 3. Okay, and in the denominator I have an x, that's a difference of 2 squares, so that factors to x plus 2, x minus 2. Okay, remember this is a squared minus b squared, factors to a plus b times a minus b. Okay, so we have it in factored form. Doesn't look like I'm going to have any holes. Okay, because I have x plus 2, x minus 2. I don't have those in the numerator. So I'm not going to have any holes. I will have a vertical asymptote. I'll have 2 of them. Okay, I'll have 2 vertical asymptotes at x equals 2 and negative 2. Okay, so we have 2 vertical asymptotes. Next, let's look for horizontal asymptote. All right. Remember, we're looking at degree of the top and degree of the bottom. So the degree of the top is 2. That's my biggest exponent. Degree of the bottom is 2. And if I go back, recall when m is equal to n, what do I want to do? I want to divide their leading coefficients. So in this case, even though you don't see numbers here, that's 1x squared. That's 1x squared. So 1 over 1 would be at y equals 1. Okay, y equals 1. So I have no holes, vertical asymptote at 2 and negative 2, horizontal asymptote at y equals 1. Let's find the x and y intercept. Remember, x-intercept is when I solve 0 equal to x plus 4 times x minus 3 over x plus 2, x minus 2. Okay, I mentioned in the last lesson you pretty much can just multiply by x plus 2, multiply by x minus 2, and since you're multiplying it by 0, you kind of cancel the denominator. An easier way to start thinking about these is really if we're trying to solve for an x-intercept, just solve the numerator. Don't worry about the denominator when you're solving these. So what makes the top equal to 0? Okay, that'd be a negative 4 and a positive 3. Okay, a negative 4 and a positive 3 coming from those. So we should have one at negative 4, 0 and positive 3, 0. Okay, I hope that makes sense. All right, and then lastly, my y-intercept. That is going to be plugging in 0 for x, so that would be a what? A 0 plus 4 is a 4, times a 0 minus 3 is a negative 3, over a 0 plus 2 is a 2, times a 0 minus 2 is a negative 2. So this would reduce to a negative 12 over negative 4 is a positive 3. So you have a y-intercept at 0, 0, 3. Okay? All right, now once I have those pieces of information, we can go ahead and sketch our graph. From here, Since a lot of these are just going to be so different, like there's a lot of different things that can change how our rational function is going to look. Once you've found all these, I want us to use our graphing calculator to help us get the shape, okay? Because they're not going to all look like, if I go back to the beginning, they're not going to all look like one of these. I had mentioned at the beginning of Wednesday's lesson that they all have pretty different shapes. So let's use our graphing calculator to kind of fill in the rest of the information for us while we have all the information we need, all the important information, like x is 2, -2 for the verticals, y is -1 for the horizontal, my x-intercepts, and my y-intercepts. Let's go ahead and see what this is going to look like. Okay, there's my y and my x. Drawing in those asymptotes. My verticals were at +2 and -2. So there's -2 for the x. Here's +2 for the x. Okay, and then we also had a horizontal at y equals 1, which is this, whoops, which is this guy. Okay, next comes our intercepts. Our intercepts are, what do we say? -4, 0, and 3, 0, and then 0, 3. So I have one at 1, 2, 3 right here. We said -4, 0, which is 1, 2, 3, 4 right here. And then also at 3, 0, I believe we said, right? -4, 0, and 3, 0. Good. Okay, so let's go ahead and plug this into our calculator now. I know this lesson's getting long, but we're almost done. Okay. Make sure I put the top in parentheses and the bottom in parentheses. We had an x squared plus x minus 12 divided by an x to the second minus 4. Okay. And we can kind of see this looks like what I have. And I know you might not have been expecting this. It's kind of like, what the heck is going on? Why do I have this random parabola here? Again, rational functions are kind of weird. So once we do all the algebra to find all those important pieces, use the graphing calculator to plug in the rest of the information. So you do see we go through 3, 0 here, -4, 0 here, and 3, or 0, 3. We have these asymptotes here, -2, +2, and at +1, you can see my graph is going to kind of stay there at 1 on the far right, and on the far left, my graph is going to stay there at 1 as well. Okay, so let's go ahead and plug that in. Okay, so this will look like that. Okay, this is weird parabolic thing here. Okay, and then this follows my asymptotes there. Okay, so that is my graph. I know there's a lot going on. Really the important part I'm worried about is that you understand how to get all the algebraic stuff here, like solve for the asymptotes, the intercepts, find any holes. That's really what I'm worried about you being able to do. Okay, I don't care that you can plug this in and graph it and sketch it. It's not art class, it's math class. So yeah, hope that was clear. Let me know if you guys have any questions. This brings us to the end of Thursday's lesson. On Friday, so tomorrow, well, not really technically tomorrow, if you're watching this on Wednesday, but on Friday, expect like a 5-question little checkup for the week that is due before Monday, basically. I'll give you the whole weekend to work on that. It'll be due Sunday night. So that's me signing out. I don't think I have anything else to say. Love you guys, miss you guys. Check you later. Peace.